if we're going to go through and look at this structure or this system as we just described, let's take a look at the copper on the reactant side. Okay. Well, the sum of the oxidation states equals the overall charge. What is the overall charge for the thing that contains copper on the reactant side? It's 0. It doesn't have a charge. So how do we set this up? Well, there's one copper atom within that. It has an unknown oxidation state, and then this has to equal the overall charge. There's nothing else to add to it, so that's it. 1 times x equals 0. What must x equal? X has to equal 0. The oxidation state for the copper on the reactant side is 0. Right? If we go through and look at the textbook or even my slides, because my slides do the same thing, they go through and say, oh, there's an extra rule with oxidation state. Anything in its elemental state is 0. I don't need to memorize that if I understand the last rule in the list, which is sum of the oxidation states equals the overall charge. Okay. We then have a new unit that we can go through and look at. Okay, the nitrate. The nitrate is an interesting one because that's going to split into a couple different pieces. We follow the same rules. Sum of the oxidation states equals your overall charge. Well, I have 1 nitrogen times an unknown oxidation state plus 3 oxygens times an unknown oxidation state. This then has to equal the overall charge, and the overall charge is again specified in the upper right-hand corner, and we know that to be -1. Okay. Now it's a question of how do we go through and solve this. This is where the rules of oxidation states kind of come into play, and ultimately they're only rules because we decided that you couldn't extrapolate from the common physical constants. Common physical constants, electronegativity. Okay? Electronegativity is the ability for an atom to steal electrons from another atom. Oxygen is more electronegative than nitrogen, which means it's going to steal electrons from nitrogen. How many electrons would oxygen steal? 2. Why? Based off of its location in the periodic table. Okay? So oxygen is going to dictate the oxidation state on the nitrogen because the oxygen was more electronegative. So its oxidation state is a -2. Conveniently, this does give us a bit of information. We now know the oxygen has an oxidation state of -2. Okay? We can then go through and solve for x. X minus 6 equals -1. X equals +5. What did we say x was? Don't tell me +5. That was the oxidation state on the nitrogen. Okay? A very common mistake made by students is that they will go through and tell me that the nitrogen has a -3. When is nitrogen a -3? When it's in an ionic compound. Okay? An ionic compound, so we're looking at the metal and the nonmetal. Okay? That's when it has a -3 charge. That's the rule that we use to tell you to memorize. Okay, I would argue that rule is a bit shaky because what are we looking at here? We're looking at nitrate with a negative charge, also known as an anion. Isn't that ionic? Shouldn't that be a -3? What does that charge go back to, or our oxidation state go back to? Electronegativity. Nitrogen bonded to oxygen is not more electronegative, so it will not take the electrons away from the oxygen. But if I bond nitrogen to sodium, sodium is much lower in electronegativity. Nitrogen's going to take the electrons away. What does it take the electrons away up to? Its common ionic charge, the -3. Kind of, sort of? This is very easy to get confused. Okay? And that's why we have to be very careful to differentiate what you're looking at within those individual pieces. Oxidation state should be something that you should just kind of fall into saying, I have to solve for it. Okay? We then go through and repeat the process on the other side. Okay? The unit I'm solving for there is copper +2. Okay? There's 1 copper. I don't know its oxidation state, and that must equal its overall charge, which is plus 2. What's the oxidation state? Plus 2. Okay? So there are systems where the oxidation state is a trivial solve because it matches the charge. That's why people conflate charge and oxidation state. But they're referencing slightly different systems. When is the oxidation state specified in a formula? Never. It's never specified. Okay? We only specify the charge when we go through and look at a formula. So the oxidation state, again, is something that we would have to calculate and understand what's coming on from within it. Make sense? We can then move to the next unit. Our next unit was NO2. And I guess if we wanted to get a little bit fancier with color coding, we'll go NO2. How many nitrogens? There's one nitrogen times its oxidation state plus 2 oxygens times its oxidation state equals 0. And this is where people will, oh, what's the charge on nitrogen dioxide, and start to look things up. If you're feeling you have to look something up, you're probably missing something. You should figure out what you're missing instead of just going, what's the charge on this thing? Kind of make sense? Particularly at this point. Why at this point more so than 2 weeks ago? Your exam is on Wednesday, right? Which means at this point you should know all of the content. So if you feel like you're having to look something up, something is missing, you need to find out what that is and start creating a memorization list of those things. Okay? Again, I'm looking at nitrogen versus oxygen. Our quote-unquote rule for oxygen is that it is a -2. So we could specify our oxygen again as a -2. We could sub that into our equation. X minus 4 equals 0. And I get X equals plus 4. What did we say X was? That was the oxidation state for the nitrogen. Okay?
So this is my question. So they're both, they both lost electrons overall.
Pause.
So,
We'll come back to that.
okay.
Because we haven't shown that at all yet. Okay, so what I would argue we do before we start moving into that is actually define what happened in each of those changes. So if we go through and look, what happened to the oxygen? Didn't change. So we don't need to worry about oxygen. There's no oxidation state change there. What's happening to the copper? It gained, lost. Yeah, it's one of those. Okay? And that does become tricky. Okay? We're dealing with a negatively charged species, the electron. Right? That's changing our input, and we're changing the positive to negative signs. So we have to be real careful with how we manipulate those to ensure that we're kind of in lockstep with it. Okay? To go from a 0 to a +2, what had to happen to the number of negative things? I had to lose electrons. And if I've lost electrons, that would be come back to that. Oxidation. Leo the lion. Right? There's our loss of electrons. Right? It's in the videos, but not this stupid oil rig nonsense. Okay, what happened to the nitrogen? We went from a +5 to a +4. What happened to the number of electrons? It gained electrons because we went from a larger number to a smaller number. A gain of electrons is reduction. So by slowing down and looking what's happening to those numbers, hopefully we don't make the mistake that they're both doing the same thing. Right? We can look at the oxidation. Our oxidation number is getting more positive. We look at the reduction. Our reduction number is getting less positive. Okay? However you want to tie that is ultimately up to you, but you do have to be careful with that transfer of electrons. Again, negative numbers are a pain in the butt to deal with. They will haunt you through everything, everywhere. Okay? Yes? Vocalize it.
For the oxygen, it started with 3 and then it went to 2, so overall it.
Oh, the number of oxygens changed.
Yeah.
Yes. What happened to its oxidation state? I don't care how many oxygens there are. I just care what happened to its oxidation state.
Okay.
Okay? All I'm asking about is the balance of protons and electrons on that atom.
Okay, that's what was screwing me up.
Okay? So what you're looking at is how do I balance the equation? Well, to deal with oxidation states, do I need a balanced equation? No. It's not relevant. Okay? And if you're looking at this, well, hey, it's an equation. I should go through and balance it and get practice. Don't, because it's not an equation you're responsible for balancing. There's extra rules that come into play that would be addressed in, say, second semester general chemistry. You don't need to worry about them. Okay? Next part that we could layer into this, because I've conveniently erased all the answer choices, would then be what would our possible answer be? Because what we're trying to describe is the nitrate, right? Which added little tidbit here, nitrate is written out as the name. So what do you have to do to be able to answer this question? Know what nitrate is. And what was nitrate? Try again. NO3 is not nitrate, that's nitrogen trioxide. Nitrate is NO3 minus 1. That charge is an intricate piece of what makes it nitrate. That's changing the balance of extra electrons within the structure. That changes everything about its potential reactivity. Okay? You need to associate that charge within it. Which means to answer this question, I'm looking at the nitrate and I'm trying to figure how it acted in this chemical reaction. Okay? Well, could I say it was reduced? That one gets a little bit wishy-washy, believe it or not. Because was nitrate reduced? Nitrogen was reduced. Okay? And this is why they introduced the ants and the ing agents, is because they're trying to get uber specific into the actual systems that's happening. Okay? Nitrate wasn't reduced, the nitrogen within nitrate was reduced. Okay? So if nitrate wasn't reduced, what happened? Something in the nitrate caused copper to be oxidized, which means the nitrate was an oxidizing agent. And while I erased all the answers, I believe that's the question that's being asked. Okay? Things to be careful of. Don't answer the question, answer the content. How do I very swiftly change this question? How did copper ion or copper metal react in this reaction? Okay? So we could say it was oxidized, or we could say the reducing agent. So you want to be able to keep track of all of those potential options. Okay? I could also just change the question altogether, okay? Or change the equation altogether. But if you've spent the time to look at all of these individual pieces, when I ask what's the oxidation state on nitrogen, you've got it. When I ask what's the oxidation state on the nitrogen in NO2, you've got it. You've built that practice to be able to answer the content across the spread, not the question. Make sense? Here's your question. You're good? Mm-hmm. Hi. Questions about this one?
So you only use the
Okay? Because in that individual unit, each of those atoms has a balance of protons and electrons. They're all contributing to the overall charge, so you have to account for each of those pieces. You want to try a trickier oxidizing or oxidation state one? I might actually have to give you some more information on this one. What's the oxidation state for carbon in acetate? So I want to address a couple things that I saw as walking around. Number one, I started to see people do carbon, then hydrogen, then oxygen. There isn't necessarily a problem with that. But that notation that we just wrote out worked when we were trying to look across a chemical reaction. Are we looking across a chemical reaction? No, so this is a single expression. Instead of doing carbon, then hydrogen, then oxygen, we have a single line. This is the sum of the oxidation states for each of the individual atoms across our overall system. Okay? So there are 2 carbons times an oxidation state for the carbon. There's 3 hydrogens times an oxidation state for the hydrogen. There's 2 oxygens times the oxidation state for the oxygen. That all together has to equal the overall charge, which is a -1. Conveniently, one of our rules was that oxygen has what charge? Oxidation state. A -2. But what's the oxidation state on the hydrogen? Okay. And that becomes an interesting one. Okay. I honestly don't remember. I think is it in the rule list that it's a +1? Okay. So if you had the rules memorized, you could run there. Right? How else did we reference what the charge or the oxidation states come from? Instead of just rote memorization, we said it came from electronegativity. And if we're looking at electronegativity, it's now what are those hydrogens connected to? They're connected to carbon. Carbon is more electronegative than hydrogen, which then means carbon's going to take the electrons away from hydrogen, which means the hydrogen's going to carry the +1 charge. And it gets its standard charge state. Oxidation state for the carbon, unknown, we still have to solve for it. So we get 2x plus 3 minus 4 equals a -1. I would get 2x equals, what is this, -1? Yeah. So then I'd add 1 to both sides, and I get 2x equals 0, and I get the oxidation state for the carbon being 0. Okay. Not the interesting answer I wanted it to turn out to be, but hey, sometimes it works. Okay. The answer I was trying to fish for was to get a fractional oxidation state. Okay. And we go, well, you can't have fractional balances of protons and electrons, and you're right. You cannot have balances of protons and electrons be fractional. But if you have multiple atoms within the structure, what we're solving for in this case is the average oxidation state. One of those carbons has a different oxidation state than the other one. Do you know how to resolve that? No, so don't stress. Follow and run the average. That's all you need to know. Kind of, sort of? Okay. Questions? What next?
Can you go over number 26?
Sure. I kind of yelled at that guy when I told him to not touch it, right? Feel bad. I'll have to send him an apology. I've never seen him before, so it wasn't personal. It was personal with the frickin' device. But that's a different system. Okay. what is found in the reaction container after solid gold is mixed with aluminum nitrate? Okay? So there's a lot of stuff going on here, and the first thing that I'm going to go through and do is delete our crutch and get rid of our potential answer choices, which is probably a good thing, because 4 out of 5, was it 5? Yeah, 4 out of those 5 answers is wrong. So if we start looking at it and we pick arbitrarily, we could easily trick ourselves into answering the wrong thing. Okay? So I'm mixing gold with aluminum nitrate. Okay, so first place to start would be, let's turn it into a chemical reaction. Okay, I take gold. If I wanted to get super nitpicky, I could go through and specify the phase. For this particular case, I don't think it matters. Generally speaking, I rarely think it matters. Plus the aluminum nitrate. Ooh, aluminum nitrate is a little bit problematic. Why is aluminum nitrate a challenging one to deal with? It's more challenging than gold because, yeah, it's polyatomic. Gold is just by itself. That was easy. Okay? But the polyatomic, we now have multiple things. We've got to deal with putting those multiple things together. So we have to be able to go aluminum nitrate, so we need to know that symbology. So we know Al is aluminum, we know nitrate is NO3. What do we know about the charge on the nitrate? It's a -1, and the charge on the aluminum? A +3. That sounded like a whole bunch of different numbers, but it's +3. Okay? Is that formula appropriate? No. I don't have a balancing of charges. To get that balancing of charges, I need 3 nitrates to balance out that aluminum. Right? I'm mixing these things. So it's saying what is found in the container. And it says reaction container, so that's nice. So that might hint that we should run a chemical reaction. Okay? What kind of chemical reaction should we run? Single replacement. And we know single replacement because we spent the time to learn what our chemical reaction types are and how this aligns to the single replacement reaction. We're looking at a element by itself and a compound where you could swap out those pieces. So we could go through and run out the swap. I'd get aluminum plus now the gold with the nitrate. What was the charge on the nitrate? -1. What was the charge on gold? Okay, this is an interesting one. Okay, so we go, oh, it was 0 on the reactant side. What kind of chemical reaction do we run? A single replacement. And what content immediately followed discussing single replacement reactions? Oxidation states. Because you're doing a redox reaction also. You're changing the balance of electrons within your individual species. So you would have to be able to predict something about that balance. This sets us up with a major dilemma because if I don't know the charge on gold in the product, how can I ensure that I've properly balanced the gold with the nitrate? I can't. Right? Which could mean one of 2 things. 1, Mike made a typo. How do you address that? Yeah. Raise your hand during the exam. Call me in lecture. Just, you're an idiot, Mike. You made a typo. Fix it. Okay? And I'll come up and I will sit down next to you and I'll look at it and I'll be like, I'm sorry. There is no typo. So what was the other option? You're missing a key piece of information that needs to get stacked into this. What are you responsible for with a single replacement reaction? Responsible for phases, okay. You're responsible for predicting them. Okay, not just what the products would be, but also that the chemical reaction happens. When we go through and look at a double replacement reaction, how do we know that a chemical reaction has happened? a change in phase. And how would we predict the change in phase?
If it's solar.
How do you know it's soluble? There's rules. So to predict a change in phase for a double replacement reaction, you use the solubility rules. Can you use the solubility rules for a single replacement reaction? No. For a single replacement reaction, we have to use something else. What do we use? Say again? You need to use the activity series. Okay? The activity series is not something I expect you to memorize. I would expect you to look at the front of the exam and look for the activity series. Okay? In that activity series, what do you need to look for? Is anybody, okay, you don't have the front page printed?
Separate.
Somebody have the front page printed so I don't have to delete all. Oh, there it is. That's all I needed. I wanted to just match the format. So we could go to the front of the exam. We find the thing that says activity series. How many of you knew right away that you needed to use an activity series? Okay, cool. So activity series is not useful information as it's written on the exam. What would be useful to add to your exam so that you know when to use the activity series? Maybe you should write SR over the top of the activity series or single replacement. So now you know right away, I'm looking at single replacement, I need to use the activity series. Add that note so that you know what's going on. It lists, where's my pen? There it goes. Most active, least active. What things do I want to look at? Okay, typically our activity series lists a bunch of metals. What metals do I care about? All I care about are gold and aluminum. Those are the only two things being involved in here. And when I go through and look at it, there might be a typo on that one. I honestly don't know. I do try and check. We see that gold is close to the least active, and we see aluminum somewhere higher. What does that mean?
It switch because it's not as reactive.
Okay? It has to do with their reactivity. Okay? The way that I like to look at activity is if they're very active, they want's a weird word for this. It's that anthropomorphized. I'm sure that went into the recording better than it came out here. Want to be with other elements. It would be the extrovert. The least active would be the introvert, wants to be by itself. So we go back up to the equation, and we go through and we use this information. Which one do you want to look at, aluminum or gold? Gold. Gold wants to be by itself. So now I can look at my chemical equation. Where is gold by itself? On the reactant side. So for this chemical reaction that we set up, does gold want to react? Nope. And if gold doesn't react, do I care how to balance it with the nitrate? Nope. 100% irrelevant. And you're like, but I could have looked at aluminum, Mike. Fair call. Aluminum. Aluminum is higher in activity. So aluminum wants to be with other elements. Where is aluminum with other elements? Also on the reactant side. What does that suggest about this chemical reaction? It doesn't happen. So what do I find in the container when I mix these two things? The same thing I started with. Which, interestingly enough, almost universally, is the very first answer that everybody crosses off of their exams. Okay? This is a very challenging question because there's very little information explicitly given to you. You have to recognize all of that information and build and use to get to that answer. Make sense? Okay. We talked about test taking strategies, so let's go back and take a look at those answer choices. Hopefully we would immediately eliminate these weird oxide ones, but then we encounter these issues up here where there are differing amounts of nitrate with the gold, which looks an awful lot like our answer. And you're like, well, it's got to be one of those because chemical reaction happened. Be careful with your underlying assumptions. Okay? So virtually all of your possible answer choices are there. You need to have confidence that you know the content to actually get the answer right. Does that help? Other questions?
Can you do
28, and then you had a question too, Alita. Is it about this?
Yeah.
Okay.
So, figuring out the answer, like, would it go back to this activity series, like, it's AU and AL, and then, like, because, like, the blue one is, like, at the bottom?
Gold is at the bottom.
Yeah, or yeah, the gold.
It's okay.
Yeah.
So gold is at the bottom. It's least active.
So it's
What
like
does that
by itself.
mean? Yeah, is that it wants to be by itself. It does not want to chemically react. That's why it's least active. Okay? Does that help? Come on, Ben. Said 28.
Yes.
This is another one that tends to stump people. I even got tutors like flipping out over this one. Cool, this is a molecule of caffeine, advanced looking structure. Everybody looks at it, panics, seizes, and flips out. Breathe. What is the oxidation state for oxygen? -2. What's the answer? -2. That's it. Done. That's the end of it. It's just -2. There's nothing else involved. Okay? I can draw any structure I want. Well, almost any structure. I'll put up an exception here in a second. And the oxidation state for the oxygen will be -2. Okay? There's a question, and then I'll draw up some potential exceptions.
Would you ever ask for a different part of that?
Would I ever ask for a different part of it? No, because you don't have the rule sets to be able to understand those. What's the oxidation state for the oxygen? Okay, let's run with it as a -2. Okay, this compound is also known as hydrogen peroxide. That is its proper formula, H2O2, just like that. If you're saying the oxygen is a -2, each oxygen is a -2. What's the oxidation state on the hydrogen? +1, and +1. What's that math turn into? Not good is a somewhat appropriate answer. -2. If you're saying the oxygen has an oxidation state of -2 in this compound, I would expect the overall charge for hydrogen peroxide to be a -2. It is not. Why? Why was oxygen a -2? Nope. We pushed on it a little bit. I gave you the context for what the rule was. Where did the rule come from? I liked where your eyes went. Electronegativity. Now we could go up to the periodic table and we could evaluate electronegativity. What is the difference in electronegativity between oxygen and oxygen? It's the same, meaning neither one can take an electron from the other one, which means they don't. It's an even split for the electrons in that bond. But oxygen is more electronegative than the hydrogen, which means it carries the -1 to deal with the hydrogen. The hydrogen is a +1 on both sides, which means our overall charge is 0. The oxygen comes in as a -1. Nope. Because there's yet another example of where oxygen is not a negative 2. What's the oxidation state for the oxygen now? It's a Lewis structure that might confuse you. O2 is our formula. Silence is a pretty decent answer. It's 0. That's oxygen in its elemental state. It's 0. Why is it not taking electrons from the other atom? Because it's flipping oxygen. It can't take the electrons from the other atom, which means there is no imbalance of protons and electrons, which means the oxidation state is 0. That's where it comes from. Okay. The really sketchy exception. How about OF2? What's the oxidation state for the oxygen there? There's an advanced question. Real close. Not +1, +2, because there's 2 fluorines. So each of those fluorines pulls an electron away. Why are the fluorines pulling an electron away? Fluorine is more electronegative than the oxygen. Our oxygen carries a +2. Neat. So if we understand where the rules are coming from, we can predict what those rules are. They aren't exceptions. What they are is we gave you something to memorize so that you didn't have to think as hard. That's all it was. Other questions? .36, similar to that single replacement reaction, because you're being asked to predict products. In the single replacement reaction, you were just given words. Now you're given an actual equation. Okay. If you have no idea what that ignore secondary reactions is talking about, that's okay. Don't worry about it. It's not a big deal. I would expect the vast majority of the class to have no clue what that's talking about. It has to be included, and we'll talk about why in a second. Okay? So we look at the reaction. If we're being asked to predict our products, what do we got to do? First step is, what's the reaction type? Okay. If it's a single replacement, we expect to see an element chilling all by itself. Do we have an element in either of those two species? It's all by itself. We don't have an element chilling all by itself, so we could shift and say, okay, double replacement, better, but you can do better. I have a hydrogen in front and an aqueous in back, which means this is an acid. And what do acids react with? Bases, which means what are we running? A neutralization reaction. A neutralization is a very specific double replacement reaction. Okay? We didn't need to know that for the sake of this question. Okay, but it's helpful for later pieces of information. So we would now go through and run the double replacement. So, predict your products. So, if we go through an exchange, what are we exchanging? You got lots of things that you could say. All of them would be valid. Say again?
The anion
Okay. Not what I expected, but that's fine. We can go through and switch the anions. Okay, so I'm going to leave the H in place, and I'm going to bring over the CO3. I'm going to leave the Na in place, and I'm going to bring over the Cl. Okay, some things to go through and point out. The 3 moved, did it not? Yes. Why? That 3 is what makes that carbonate, CO3. It's part of the identity of carbonate. Okay? So I have to keep it with it, otherwise I'm changing its identity. What about that 2? Did that move? It did not. Why not? It's still a subscript. The intent of that 2 is the amount of sodiums to balance carbonate. When I go over and look at the product side, the sodium is not with carbonate, which means I don't move the 2. It is possible that I need a 2 there, but that 2 would appear for a very different reason. Kind of, sort of? Why would I need a 2 with the sodium in the product side? To balance. Right? So if I'm being asked to predict the following products, or which of the following is a valid product, I need to go through and ensure the product I'm showing is properly balanced. Okay? What is the charge on chloride? A -1. What is the charge on sodium? A +1. Is that a proper formula? Yes. Okay. Right away, we could see a potential answer choice, Na2Cl2. Why did that happen? You brought the 2 across, then we're like, oh, it's not balanced, so I'm going to put another 2 in there. You need to move the numbers with reason. We also got to look at our HCO3. What is the charge on CO3? That's a -2. What is our charge on hydrogen? A +1. Is our formula balanced? No. What do I need? I need 2 hydrogens. I need H2CO3. I've now predicted my proper products, and I can now go through and look for a potential answer that matches. Again, you go through and look at those answer choices, you will note that almost all of them have some foundation in how you could have done that chemical reaction. So again, you need to know what's going on, because a guess is only going to net you about 20%. Make sense? Okay, so in this case, our answer is, must say I heard an E? Yeah. Okay. Why ignore secondary reactions? H2CO3 is a special compound. It's a compound that you will actually look at after spring break. I don't think you see it this week in lab, but you'll see it next week. Okay? It's something that you're very familiar with. H2CO3 is commonly found in all of our sodas. It's known as carbonic acid, which you should be able to name. Okay? As carbonic acid, it is an acid, so it does eat through things. Allegedly, police officers will keep this in their trunks, so if they have to clean blood off the road, they can just throw the carbonic acid on it. Easily found in sodas. They keep a 2-liter thing of Coke around. Anybody confirm that? You say no, it's not true? Yeah. What's that? Okay, yeah. I thought it was a little weird of a statement to begin with. Okay? But it is still an acid. What does that carbonic acid turn into? What phase is H2O? It's a liquid. What phase is CO2? A gas. Why is your soda bubbly? Carbonic acid. Okay. What they do is force CO2 into the solution. The CO2 reacts with water to form carbonic acid. As soon as you release the cap, that CO2 starts to bubble out of the solution. Okay. It's all based off of carbonic acid. Okay. Another fun story, you know where else carbonic acid is used? Cellular respiration. It's how we remove carbon dioxide from our muscles to our lungs so that we can expel it. It's all moving through bicarbonate. Neat. Which we'll talk about much later in the semester. And if you're a nursing major, you'll talk about it a lot in your other classes. Okay. Next question? Or any questions on that? Universally, I would say pretty much everybody trips up on word problems. Nobody liked word problems in a math class, and guess what chemistry is? It's a giant flipping word problem. Everything we do is a word problem, so it's all about how do you extract the information out of the English language. It's not chemistry's fault, it's English's fault. You're just bad at English. Translate into chemistry and everything becomes beautiful. That was a subtle dig. That wasn't intended to be that bad. It's a little harsher than I expected. Okay, so with this particular question, since we're being asked about densities, there's a lot of numbers floating through this. What I would immediately try and do is turn this into a picture. I'm looking at a glass cylinder containing all of these things, so I'm going to create a glass cylinder and start to piece this together. Okay, I would start with my first two, density 13.6 and a density 1.49. Before I start drawing them in there, I do have to know a piece of information. What's that piece of information I need to know?
Does density work?
What's that?
How does density work?
How does density work? That's a good description. If I put these two things into the cylinder, what happens? They separate. They'll separate into two layers. Great. Which layer is which? Okay, and this becomes the fun one. Which would you rather get hit with, a pound of feathers or a pound of lead? Pound of feathers. Which one weighs more? This isn't about heaviness. It's about density. Okay, so the more dense settles to the bottom. So it's a surprise I grew so tall. Thank you. Okay, so our 13.6 is at the bottom. Okay, relative to those two, 13.6 represented my mercury. The orange should be above that, my 1.49, which was my chloroform. Okay, I get a little bit lucky because I just started guessing and hoped they were in proper order. Water is a density of 1. There's my water, and then my ether comes in at a density of 0.078 with my ether. The wooden block is now dropped into this, a density of 1.6. That density of 1.6 sees that 0.7 and does what? Passes straight through it. It then sees the 1. What does it do? Okay, passes straight through it. It then sees the 1.49. Also going to pass straight through. It sees the 13.6. Not going to pass through that. There's my wood block. So now what I've got to go through and do is find the answer that matches that. On top of the ether layer. No, this is where I ended. This is my answer. So it's not on top of the ether. On top of the water? No. On top of the chloroform? No. At the bottom of the cylinder? No. On top of the mercury. Okay? So it's really just coming down to probably this one piece right here. The more dense is at the bottom. If you got that, the rest of it falls in place. Yes? In just a second. Are we good with that? Okay. This is a conversion problem that has all sorts of shortcuts to it. The intent is not that you know how to convert the mass of beans, because ultimately I just made up these numbers. Okay, so I have no idea if any of these things are true. What we're actually testing on is your process. How do you go through and solve? What we've been talking about with all of our solves is first identifying what you want and then noting what you have. Okay? Typically, those things are not the same. Welcome to life. Which means you have to do a conversion. In that conversion, you have to convert what you have into what you want. Okay? Lots of people want to go into nursing. Do you have the prerequisite skills? No? So what do you got to do? take classes. Okay? That's probably not what you wanted to do, but that's what you have to do to build that conversion system across to make sure you've got those prerequisite skills. So we go back to this question and say, okay, what do I want? I want beans. Okay? Now what do I have? And this gets interesting because if we read through that question, we're actually given a couple halves. How do we know which halve to use? Well, that's going to come down to the rule sets that you're trying to navigate. Okay? If you wanted to go into nursing, are you taking a bunch of... It's going to get insulting no matter what I do. Comic book design classes. Why not? That's not necessary to use on that path. So what you're trying to do is find the things that are useful that allow you to navigate towards that end goal. Because the English language is a bit nasty, it can be helpful to go through and pull the stuff out of that system. Okay? So we got coffee beans shipped in 2.3 kilogram packages. So I got 2.3 kilogram packages. Okay, what else do I have? I know 1 bean equals 1.0 centigrams. Since I know I want beans, I now have to decide, what do I have? Well, which halve should I use? The halve that I should use should closely resemble what I want. That's the intent behind this. So I go back and I look at that given information. Kilogram packages doesn't look like beans to me, but 1 bean looks pretty dang close. So what I'm going to go through and do is set up my conversion where I've got bean in the numerator. Why do I want it in the numerator? Because that's where I want it to appear in the numerator. This is related to centigrams. The numbers that go with it come from that expression. 1 bean, 1.0 centigrams. I can now look at this and say, is this what I want? It's half of what I want. I also have this centigram thing that I don't want. So what do I need to do? I need to somehow do a conversion to get rid of it. In that process, I want centigrams in the numerator so that those units can cancel. So I go back to my given information and say, do I have centigrams? And this is generally speaking where everybody goes, yeah, I do have centigrams right here. You just used that information. And if you bring it in again, all you're going to do is undo the work you just did. Okay? Absolutely fair, you could do that, but I guarantee you're going to end up reusing the exact same thing again. So it isn't worth messing with that one, which means ultimately I don't have centigrams given to me, which means I'm going to have to do a conversion. Okay? What do I want to convert to? Dollar bills. I can convert centigrams to dollar bills. Okay? I can convert it to anything I want, but the question is, what is useful for me? Back to my given information, I have kilograms. A centigram to kilogram conversion would be awesome. Fantastic, I can just plug it in. Do I know that centigram to kilogram conversion? Okay. If you do, by all means, go ahead and use it. Generally speaking, people that think they know about 50% of the time are wrong. Okay? We know we need this conversion, but the only conversion we know we should know, it's a bit silly to say, but I said it anyway, would be centigrams to grams. This was something you were told that you needed to have memorized. Okay? In that thing that you were told to have memorized, you were told that centi meant 10 to the negative 2. 10 to the negative 2, our power of 10, will always go with the core unit. Okay? Do you not like that conversion? Would you rather use 100 centigrams is 1 gram? By all means, go ahead and use that because it is equally valid. The problem is you've memorized more information than I think is necessary. If you've got it right, then by all means run with it. What happens? The centigram unit cancels. Hooray, that's what I wanted to do. Do I have my problem fixed? What did I introduce?
Grams.
Grams. Do I want grams?
No, kilograms.
So I need to cancel the grams. Do I know my grams? No. Again, I cycle back to that given information. No, I don't, which means I need to convert the grams to something else. I do know I have kilograms, so if I can convert grams into kilograms, I'm in a sweet spot. Do I know that conversion? Hopefully you do. Power of 10 is 10 to the third, goes with the core unit, which would be grams. Okay, what happens? The gram unit cancels. Great, hallelujah, that's what I was trying to do. Have I solved my problem? No, because I still have kilograms, so what do I need to do? I need kilograms to cancel, so I go back to my given information. Do I have just the kilograms? Yes. I'm told I have 2.3 kilograms. Number in the denominator is 1, so it does not change the meaning of the number or the unit. Now I have my calculation set up. It's now just a question of entering it into the calculator. This question, believe it or not, is really zeroing in on those people that do King Henry died drinking chocolate milk while sunbathing in Africa, whatever the hell that stupid statement is. Okay? Because generally speaking, people that use that can't use it consistently correct. Okay? And so it comes down to you clearly I don't, because I'm pretty sure it doesn't end in Africa. Okay? There are certain things that you should memorize. Knowing that Henry stands for hecta is useless information. Okay? Does it have the mnemonic on it?
Yeah, it has everything on it, but if you're curious what it says.
What is this stupid statement?
I
King Henry died. Oh, I got died. Ugly drink chocolate milk. See, with 3 monks. I give up. Okay, with that, we're done.